Alright, so today we're going to be starting our new extension 2 topic of the nature of proof. So this relatively new topic in the course helps us develop our ability to convey convincing mathematical arguments, and it really is developing our ability to go into the path of pure mathematics, which is kind of maths for the sake of maths, over a lot of other topics such as mechanics in Extension 2, which is more applied mathematics. So all topics in Extension 2 rely on our ability to construct logically sound and convincing proofs. In the nature of proofs, we're going to focus on logic and alternate ways to prove things where direct proofs such as induction are not appropriate. Okay, so a statement in mathematics is an assertion that can either be true or false, but not both. So some examples are 6 is an even number, a true statement, or 6 is an odd number, a false statement. Often we're going to use letters to represent these statements. So the sum of the first positive integers, the first n positive integers, we might say is p of n. Two of the most important things in this topic that we're going to learn at the very beginning that you mightn't have seen before, I have shown you in Extension 1, but we're going to officially learn what these are now, are our two quantifiers. Number one, and I say two, there are many more than this, but number one is the universal quantifier for all. So some statements are true for all values of a variable, true or false for all values of a variable. And we can abbreviate this with the symbol for all, which is an upside down A. So for example, this sentence would read, for all real numbers x squared is greater than 0. That means that all squares of any real number must be non-negative, and we know that's true. That's why we can use the for all symbol. And the other quantifier, the existential quantifier, is there exists a backwards E. So the term there exists indicates that there is at least one number for which a statement is true, not necessarily all numbers. So for example, this sentence would read, for all x for which x squared is odd, for all, there exists x for which x squared is odd, is saying that there is at least one value for x for which x squared is odd. We know that's true. 3 squared is 9 and 9 is odd. Right. So this example here, we're going to insert the quantifier that would make this statement true most of the time. So m squared is greater than 0. That is always true. So we're going to put the for all quantifier. So we could say for all m squared is greater than 0. Part B. m is equal to 0. If we put for all, that would be telling us all real numbers are equal to 0, which we know is false. So we're going to put there exists. The number 0 is 0, so there exists m such that m is equal to 0. For m on 2 is an integer. Well, we know that if you divide all numbers by 2, you're not going to get a whole number. So we know that that's not true. We can't put for all, but it is true for some numbers. It's true for all of your even numbers, so we're going to put there exists. Part D, we've got for m, sine of m is between -1 and 1. Well, sine of anything has to be between -1 and 1, so it's for all m. Any value of sine is going to be between -1 and 1. Okay. Example 3, we're translating these following statements into everyday language. Now that's missing a square root there. So also determine whether this statement is true or false. So part A is saying there exists x belonging to the real numbers such that x squared is equal to the square root of x. That would be that sentence in everyday language. So there exists x belonging to the real numbers such that x squared is the square root of x. That is actually a true statement because 1 squared is 1 and the square root of 1 is 1. So there does exist at least one number, so that is a true statement. Part B says, for all integers n, the number 5n is even. So that would be that in everyday language, and that is a false statement because any number multiplied by 5 is not going to be even. Okay, the negation of a statement. The negation of a mathematical statement is a statement that is only true when the original statement is false. So for example, the negation of x being greater than 0 is x is less than or equal to 0. It's kind of like the opposite of a statement. A few important things. The negation of P and Q, well, P and Q would be two circles in a Venn diagram overlapping, and it would be the center where those two circles overlap would be P and Q. The negation is not P or not Q. So that would be the opposite, not P or not Q. And the negation of P or Q is not P and not Q. So we can see that when we're negating, the and the ors change. Negate the following statements. We've got n is divisible by 2 or n is divisible by 3. Well, we might say that first of all, the opposite of being divisible by 2 is not being divisible by 2, and the opposite of being divisible by 3 is not being divisible by 3. So we might say n is not divisible by 2. Now this is an or, so and not divisible by 3. Okay, we're going to negate x is greater than 0 and x is less than 5. So we're thinking, what is the opposite of being greater than 0 first of all? Well, that's x is less than or equal to 0, or this becomes an or x is greater than or equal to 5. So we're taking the opposite, basically the opposite, and changing the n to an or. That is the negation of that statement. Okay, examples and counter-examples. So in part A of example 3, it was claimed that the statement, there exists x belonging to the real numbers such that x squared is equal to the square root of x is true. And to justify a claim, a single example was provided. Now, if we're just proving that something exists, there exists, and we're using that existential quantifier, one example is enough to prove that statement. Because that quantifier, a backwards e, there exists, only means that we have to only have a minimum of one number. So if we show there is a minimum of one number, we've proven that statement. Now in example 3 part B, it was claimed that for all integers n, the number 5n is false. Now that for all symbol is what we call the universal quantifier, and it says that for all real numbers, this statement is true. So to disprove such a statement, all you have to do is provide one counter-example, and then that statement is no longer true because we could not use the for all symbol. So providing a single counter-example is always sufficient to prove that a for all statement is false. Okay, negating statements involving quantifiers. So consider the negation of the statement for all real numbers x squared is greater than or equal to 0. If this is not the case, that every square real number is greater than 0, then it must mean that there is at least one real number whose square is less than 0. Now we know that's not true, but we can still negate a statement and get some sort of expression, but it's just a false expression. So the negation of this statement here, for all real numbers x squared is greater than 0, is there exists a real number x such that x squared is less than 0. So this quantifier has become a there exists, and we've negated this statement by making it less than 0. So notice how the negation of for all is there exists. The reverse is also true. So for example, the negation of the statement there exists a real number x such that 3x is equal to x is for all real numbers x, so this there exists has become a for all, 3x is not equal to x, so we've taken the opposite of that equal sign. Right, so we're going to determine the negation of each of these statements involving quantifiers. So, for all integers n, 2n is even. So we're going to say the negation is there exists an integer n such that 2n is odd or not even. So the opposite of even is odd. So there exists an integer n such that 2n is odd. Part B, there exists a real number x such that x squared is equal to minus 1. Well, the negation of this statement would be for all real numbers x squared is not equal to minus 1. And part C, there exists an integer n such that n is even and n is prime. Well, the negation becomes a for all integers n, and we could say for all n belonging to the positive integers, or actually not positive, for all n belonging to the integers, n is not even, so n is odd. This becomes an or n is not prime. Now we're not going to say composite here because we've still got the number 0, which is neither prime nor composite. Now we were asked to comment whether these are true. So the original statement is true because any number multiplied by 2 is even. And the negation is false because there does not exist any integer such that 2n is odd. Part B, we've got for all real numbers x, there exists a real number x such that x squared is equal to minus 1. That is false, but the negation is true. All real numbers x, x squared cannot equal minus 1. That's a true statement. Part C, there exists an integer n such that n is even and n is prime. That is true. 2 is both even and prime. Let's have a look at the negation. For all n belonging to the integers, n is odd or n is not prime. N is odd or n is not prime. N is odd. I think that's a false statement there. N is odd or n is not prime. That's definitely not true. Because that's not true for all n. That might be true one of the time, but it's definitely not true for all n. Okay, implications / conditional statements. So to say that P implies Q means that if P is true, Q must be true, and we call it an if-then statement. Now we are not saying that Q is always true, we're just saying that if P is true, then Q must be true. So these are what we call Euler diagrams, so we can see that here, if P is true, then Q is also true. But if Q is true here, that doesn't mean P is true. Now, if you are in the P ellipse, then you must also be in the Q ellipse. So we're going to say P implies Q. That is, if P is true, Q must be true. And that's the symbol we use there. P implies Q. Now we can also write the opposite. So Q implies P. So that is the opposite of that basically. So Q implies P, or P, Q with then a backwards implication symbol, P. And that's the same as P implying Q. So we can see here, if Q is true, then P is going to be true at the same time. Okay, so consider the following statements. We've got P, n is a positive integer, and then we've got Q, n is even, an even number greater than 0. Which of the following statements is true? Now to do this question, I would draw one of those handy little Euler diagrams. So let's go, we've got our Q being an even number, and p is a positive integer. Okay, so p implies q. So if we've got a p, does that mean q is always true? No, it doesn't. Q implies p. Well, if I've got a q, does that mean p is true? Yes, any q here, or it's always going to be inside that p circle. So yes. Does q imply p? That's the same thing as what we just said. So yes. P implies q. That's the same as part A. No. P is implied by q. Well, if we've got a p, does that mean p is implied by q? That is true. If we've got a q, that means p is true. So yes, that is true there. Example 6, rewrite the following conditional statements using the implication symbol. So if n ends in 0, then it is even. So we've got if n ends in 0, then it is even. That would be that, using that symbol there. If n ends in 0, then n is even. Part B, for all integers n is greater than 3 is a sufficient condition to conclude that n is positive. First of all, that is a true statement. If n is bigger than 3, then it has to be positive. What is that thumbs up doing there? Okay. So we might say if n is greater than 3, that implies that n is positive. And part C, if n is greater than 3, n greater than 3 is necessary if n is greater than 4. So that's saying that if n is greater than 4, then n is greater than 3. So n being greater than 4 implies that n is greater than 3. We can't say that opposite way around is true. We don't necessarily know that if n is greater than 3, then n is greater than 4. So we can't go back the opposite way. That's quite important, especially when we get to the idea of logical equivalence. Logical equivalence is when we have an arrow on both ends. So one implies the other, and the other implies the first thing. But in this case, the opposite is not true. Okay, the converse of a statement. The converse of a conditional statement is a statement obtained by swapping the statements on either side of the implication symbol. So for example, if I had the statement, n is a multiple of 10 implies that n is an even number, the converse would be if n is an even number, n is a multiple of 10. So we've literally just gotten this and swapped it and put it first. The other thing we can do is take the contrapositive of a statement. The contrapositive of a conditional statement or an implication statement is that if the statement is obtained by swapping the statements on either side, but also negating both statements. So if we've got the statement n is a multiple of 10, then n is an even number. Pardon me. The contrapositive will be first of all swapping those two statements, but then negating both of them. So n is an even number becomes n is not an even number, and n is a multiple of 10 becomes n is not a multiple of 10. Now in this topic and in mathematics, instead of saying not, we often use this symbol here. So n is not even, and n is not a multiple of 10. Okay, so example number 7, we are going to write the converse, the contrapositive, and the negation of the following conditional statements. Okay, I might just talk about these because it is quite a lot of writing. So we've got the statement, if n is a perfect square, then n is divisible by 3. So let's first of all talk about whether the original statement is true or false. If n is a perfect square, then n is divisible by 3. That is definitely a false statement because it's saying that it's saying that all perfect squares are divisible by 3. 16 is a perfect square and it's not divisible by 3, so it's a false statement. Now the converse of this statement would be, if n is divisible by 3, then n is a perfect square. So we're swapping them around. So if n is divisible by 3, then n is a perfect square. Again, that's a false statement. 12 is divisible by 3, but not a perfect square. Now, the contrapositive of this statement would be, if n is not divisible by 3, then n is not a perfect square. Likewise, this is a false statement. So n is not divisible by 3. Let's think of a number not divisible by 3, 5. Then n is not a perfect square. That is quite true there. And then is not a perfect square. That is true there. Let's think of something else that might not be true. 16. 16 is not divisible by 3, but it is a perfect square. So therefore, this statement is false. Now, the negation of this statement would just be, there exists n being a perfect square that is divisible by 3. Now, that is a true statement, because there is a number that's divisible by 3 and a perfect square, 9, for example. But the reason this is a true statement is because it's not saying for all n being a perfect square, it's just that there exists. Okay, De Morgan's law. Now, everything we've been learning are known as De Morgan's laws. So, where in this question we're asked to shade the following Venn diagrams to show De Morgan's laws. So, the negation of P and Q is not P or not Q. So we've got not P and we've got not P and Q. The negation is not P or not Q. So first of all, P and Q is the middle. So not P and not Q would be outside here. Not P and not Q. So not P and Q would be that there. Now the negation of that, not P, would be not P or not Q. Not P or not Q. Now not P is all of this here. And not Q would be all of this here. So not P or not Q is really everything apart from the center of that graph. Okay, the negation of P or Q is not P and not Q. So the negation of P or Q is not P and not Q. So let's look at not P or Q. So not P or Q. Now P or Q is that there. So not P or Q would be the red outside of it. Now the negation is not P and not Q. So not P and not Q. Let's have a look at not P. Not P is all of this in red, and not Q is all of this in blue. So not P and not Q would just be where the red and blue overlap, so it's the outside of that Venn diagram. Okay. Logically equivalent statements. So recall that a conditional statement n is a multiple of 10 is an even number is true, but the converse n is an even number and n is a multiple of 10 is not. Sometimes, however, conditional statement and its converse are both true. As an example, notice that if x is 5, then 2x is 10, and conversely, if 2x is 10, then x is 5. So this means that for the two statements, x is 5 and 2x is true. Whenever one is true, the other must be true. So we'll say these statements are logically equivalent, and we use this symbol here. It's the implication symbol with the arrowhead on either side. Right, so we're going to rewrite this sentence here using the logic equivalence symbol. So for an n to be divisible by 5, it is both necessarily and sufficient that n ends in either 0 or 5. So if n is divisible by 5, then it ends in 0 or 5. Let's see if this is a true statement. So if n is divisible by 5, yes, it does have to end in 0 or 5. And if a number ends in 0 or 5, then yes, it is divisible by 5. So this is a logically equivalent statement. Okay, that is an introduction to the nature of proof. I hope it makes sense.